Previously on prostaglandins. Okay, so we talked about the difference between prostaglandins. We mentioned prostaglandin A, B, C, D, E, and F. And we said that we need to take a look at these structures and talk about really the main difference between them and why we have so different many different variations of them. So that's what this video is going to focus on. It's going to take a look at the structural properties of these prostaglandins. And we're going to look at A, B, and C first. And what we're going to do is what you're already seeing on the screen are multiple different cyclopentane rings because this is how prostaglandins start out. And then you see R1 and R2 on each one of them. And the R1, of course, represents the 7-carbon chain, and the R2 represents the 8-carbon chain that we've discussed before. I'm just too lazy to write it out. So this is typically what we do when we draw these prostaglandins because the focus is on where they're different. And it doesn't do me any good to draw 7 carbons up at the top and 8 carbons down at the bottom when I really only want to look at the differences between these prostaglandin molecules. So in the PG, A, B, and C family, we said that we always have a carbonyl and we always have a double bond. And we've got to figure out where the carbonyl and the double bond is located in every one of these. Okay, so the carbonyl is located in the same spot. Here is the 7-carbon chain that would be up here at the top. The carbonyl is the neighbor next door. So in each one of these prostaglandin structures, that is where the ketone is going to be located. Please note that it doesn't really change. The position stays the same in all of the prostaglandins. So it's not the position of the carbonyl that determines this. It is the position of that double bond that distinguishes between PGA, B, and C. And that's something that we mentioned previously. Alright, so let's take a look at our first variation. We're going to call this PGA, and PGA has a double bond that's right here. So right across from the R1 and R2. And this structure is called our PGA, prostaglandin version A. With prostaglandin version B, our double bond happens between the two alkyl groups. So this is PGB. So PGA is opposite of, and PGB is between the R groups of R1 and R2. And this leaves me with PGC. And PGC happens down here at the very bottom. It's opposite of the ketone. So PGC is there. This now goes into the PGD and E category. So the PGD and E also have something very in common, and the PGDs and E's are made up of ketones and alcohol groups. So not a double bond, but an alcohol group that's there. Where is this ketone group? Well, in the PGD, so let's pretend that this is R1 and let's pretend this is R2. In the PGD version, PGD, we have a double bond that's down here now instead of up here beside of R1. So we see the PGD molecule switch the position of that ketone. What was a double bond O up here is the alcohol group now. So this makes a PGD for us. And then the PGE, the R1 and R2s are going to be here. And the PGEs will have the double bond O at their proper location, and then the OH groups that are here. So PGE is what we see. So these are the 5 classifications. We had a 6th one, and the 6th one was called PGF, right? So let me scroll back up here to the top, and let me draw the 5-membered ring, and we see an R1 group and an R2 group. And with the PGFs, we said that these were 1,3-diols. So what that means is that up here at the top I find an OH, and down here at the bottom I find an OH at both of those spots. And this is the PGF. We also talked about the differences between alphas and betas, and we took a look at what the numbers, we said that sometimes there could be numbers involved in this whole mess and setup. Uh, this is something that we'll briefly mention. It's not something that we'll mainly focus on, but if we have a subscript on the PG abbreviation, the subscript gives me an idea of the total number of double bonds in the side chain. Okay, so for instance, let's say that we have a five-membered ring here, and then here at the top, this is R1. Let me go ahead and draw it out. 1, 2, 3, 4, 5, 6, and 7. So COOH is here. Let's say that on this molecule or this atom we have a double bond O. Let's say that there's an OH group that's here. And then on this position, this is my R2 group. So this is 1, 2, 3, 4, 5, 6, 7, and 8. So typically 8 was the skeletal structure. It's 8 here as well, but that doesn't mean that it can't have other things on it. So let me put a OH group that's here, and let me put a double bond that's there. Okay, so this is a PGE molecule, or a PG molecule, prostaglandin. I need to maybe figure out what type of prostaglandin that I have. So how would I do that? Well, that means you need to take a look at the head, and you need to look at double bond O and OH. So double bond O and OH. So that's not a PGA, it's not a PGB, it's not a PGC. If I look, it looks like a PGD or a PGE. And the way that this template is made, my double bond O is up here at the top beside of my 7-carbon chain, and my OH is kind of pointed down here at the bottom, and my OH is pointed down at the bottom. So this looks like a PGE molecule. So it's a PGE variation, and with this particular molecule I can give you more insight of what the structure is like, and I can do a subscript of a 1. And that subscript of a 1, this number here, that number gives you an idea of the double bonds that are included in the actual side chains. Not in the ring, but in the side chains. So that is PGE1. Now, what if there was a double bond up here at the top? Well, that would be called PGE2, because there's two double bonds, one here and one there. So if you see a number, that number is representative of how many double bonds are in the actual side chains themselves. Keep in mind, it is not the ring. You do not count the number of double bonds in the ring if they're there. It's only the side chain, and that is it, nothing more. We also talked about alpha and beta. So we said sometimes we can see an alpha and sometimes we can see a beta being involved in some of these abbreviations. So for instance, PGF2 alpha. So what that means is that we have a PGF molecule. So here's PGF. And what I'll do is that I'll erase R1 and R2, and I will add on the proper number of carbons. So 1, 2, 3, 4, 5, 6, and 7. And then 1, 2, 3, 4, 5, 6, 7, and 8. So there is my PGF template. And PGF templates, let's say that this PGF molecule has an OH group here, and let's say that it has a double bond here, and let's say it has a double bond there. So this is my PGF2, right? My PGF2, there's 1 and there is 2. Now this OH group is there. I didn't tell you that it was there. Would I expect for you to know that it's there every time? Not necessarily, but I drew it because I knew what this molecule looked like. So I'm going to keep it there. But PGF, there's my template. 2 basically means 2 double bonds, so I'll just put them anywhere. That's where I'll put them because I know that's where they'll go. And then the alpha that we had in that particular instance. The alpha and the beta specify the configuration of the two OH groups in the PGF. So if I get alpha, that is a cis, and if I get beta, that is a trans. So alpha is the cis notation, beta is the trans notation. So what that means is that in this molecule I need to provide you some stereochemistry. So what I'll do is that I'll point these in the same direction. So I'll put both of them on a solid wedge and not a dashed wedge. So that is, or I could put both of them on a dashed if I wanted. As long as both of them are pointed in the same direction, that is cis. So there's PGF2 alpha. The 2 means 2 double bonds in total of the side chains. The alpha means that for this particular PGF molecule, the OH groups are pointed in the same direction. If it was PGF2 beta, the OH groups would point in opposite directions. Okay, so this is summing up some of our PG structure. You're seeing very similar things in all of the structures. They're just slight modifications on every one of them. Now, the answer or the question that you might have is, where do the PGs come from? Well, the PGs are made in your body, and they are made from a very specific source, and this is coming from arachidonic acid, a fatty acid that we learned a couple of videos back. So all of the PGs come from fatty acids, and the fatty acid that they use is arachidonic acid. So very, very important. Arachidonic acid is the precursor to all of the PGs. The arachidonic acid reacts with something that we call cyclooxygenase, and that makes the ring structure, or the beginning of the ring structure, with the 7 and the 8 carbons in total. Arachidonic, if you take a look at the PGE structure, right, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. There's 20 total carbons in PGEs. Arachidonic acid is the fatty acid that had 20 carbons involved. Hello, that's why we use it. So arachidonic acid just basically gets fused together to make the cyclopentane ring, and then it has these two tails, one of 7 and one of 8. 20 carbons in total. Arachidonic has 20 carbons in total. So it uses cyclooxygenase, it uses hydroperoxidase, and after several synthesis steps, you will start to see the production of some of these prostaglandins or prostacyclins or thromboxanes that begin to form because of it. So that's really all that we're going to say about PGs. They are made from arachidonic. You need arachidonic in your diet. If you don't have arachidonic, then you can't produce prostaglandins. And we've already seen that prostaglandins really play a role in some important features of everyday living, and that's something that you want to make sure that you are producing and that you are controlling, are your PGs. Alright, so in the next video we'll take a look at how to slow down PGs, because sometimes I don't want the pain, sometimes I don't want the inflammation, sometimes I don't want the fever, and I want to get rid of all of these symptoms so that way I feel good and I can go to work or school or do lab work on that day, right? So in the next video we'll talk about how to inhibit PG production, and that makes me feel much better, literally, when I do that.